Section: Introduction. In this section, we discuss recent advancements in agents based on large language models, LLMs, that have shown impressive abilities in tackling complex tasks using external tools. We focus on search agents, which specialize in gathering and analyzing information through search engines and other tools. These agents interact with external resources to find answers to user queries. The simplest search agents use prompt-based methods that take advantage of pre-trained LLMs. However, these methods have limitations, such as difficulties in optimizing prompts and workflows, and their performance is restricted by the capabilities of the underlying LLM. As tasks become more complex, these limitations become more pronounced, leading us to explore fine-tuning techniques. Reinforcement learning, RL, has proven effective in traditional agent training and is now being applied to enhance LLMs, particularly in their reasoning skills. RL allows an LLM to explore different paths to find the correct answer, generating reasoning steps and retrieving information through tool usage. This approach shows promise for training high-performance search agents. Some research has focused on using RL to train search agents, like Search R1, which improved retrieval by integrating advanced search interactions with complex reasoning. However, existing datasets for training primarily consist of simple question-answer tasks, which do not adequately prepare agents for advanced search strategies, such as breaking down tasks and analyzing uncertainty. To tackle the shortage of quality training data, we created a data synthesis pipeline powered by LLMs to generate high-quality RL training data. We start with a basic question-answer pair and progressively modify the question or add relevant information to create more challenging variations. Each synthesized question undergoes a thorough quality check to ensure it is clear, difficult, and authentic. As training tasks become more complex, agents cannot rely solely on search tools. They often need to navigate multiple pages, analyze content, and engage in extended reasoning, which involves many tool interactions. This complexity introduces challenges for RL training, especially in traditional systems that collect trajectories in batches, leading to inefficiencies. To improve efficiency, we implemented a fully asynchronous RL training pipeline. This means that each trajectory is generated independently, allowing for continuous progress without waiting for the slowest trajectory to finish. Additionally, we decoupled the rollout and training processes, enabling long trajectories to span multiple model versions and maximizing GPU utilization. By combining large-scale training with high-quality data, we present ASearcher, an end-to-end RL-optimized architecture. ASearcher trains agents to conduct multi-turn interactions using various tools while maintaining strong reasoning and long context understanding. We evaluated our approach with the Advanced Reasoning Model QWQ32B, achieving state-of-the-art performance on challenging benchmarks like XBench, Deep Search, and Gaia. Our findings indicate that zero-shot RL training on our synthetic data improves accuracy significantly compared to open-source datasets. This highlights the robustness of the data we constructed. We also clarify the distinctions between deep research agents, search agents, and deep search agents, focusing on their search call frequency and whether they generate final reports. In summary, ASearcher is an open-source project designed to train deep search agents using reinforcement learning. It employs fully asynchronous training to enhance efficiency and incorporates a data synthesis agent to create high-quality RL question-answer pairs. ASearcher unifies reasoning, planning, and long context capabilities, allowing it to handle numerous search queries and process extensive documents effectively. Our results demonstrate that ASearcher achieves superior performance and enables agents to learn robust search strategies. Section Summary. In this section, we discuss the development of ASearcher, an open-source project designed to train deep search agents using reinforcement learning, RL, to conduct in-depth searches with multiple tools. We address key challenges in training, such as the inefficiencies of traditional RL systems and the lack of high-quality training data, by implementing a fully asynchronous RL training pipeline and a data synthesis approach that generates complex question-answer pairs, ultimately achieving state-of-the-art performance on challenging benchmarks. Section: Preliminary. In this section, we outline our approach to multi-turn agentic reinforcement learning, based on the Markov Decision Process (MDP) framework. An MDP consists of a state space, action space, transition probabilities, a reward function, and a discount factor. The state space includes history, search results, and retrieved web pages, while the action space consists of tokens generated by our agent. We can extract tool calls from actions using specific tags. The transition probability describes how the state changes after an action is taken, and we assume a sparse reward setting where rewards are given at the end of the process. We utilize rule-based functions or a large language model as our reward function, with the agent generating actions based on the current state. Next, we discuss the limitations of existing open-source approaches through a case study of a challenging question from Gaia. We analyze two models, Search R1 to 32B and Search O1, QWQ. Our example involves identifying a specific animal based on 4 unknown variables. The agent must first determine the species from a clue about its genus, find a relevant 2021 article, and locate papers by 2 mentioned individuals. This task is difficult due to high uncertainty, the need for precise information extraction, and the potential for misleading answers. We observe that existing online reinforcement learning methods struggle to learn complex search strategies. For instance, Search R1 to 32B fails to break down the query into manageable parts, leading to vague queries and unsupported conclusions. Additionally, the model's limited turn count restricts its ability to utilize tools effectively. We also note that prompt-based large language model agents can falter due to their inherent limitations. While Search O1, QWQ, can identify the species and relevant articles through numerous tool calls, it often overlooks critical information, leading to incorrect conclusions. Even when it finds relevant data, it can be misled by prior errors and fails to verify its findings. Finally, we analyze our end-to-end reinforcement learning agent, ASearcher Web QWQ. This agent effectively decomposes complex queries into precise ones and focuses on one website at a time, summarizing all relevant information. When direct results are unclear, ASearcher can infer the correct answer by connecting information from different papers. After identifying the answer, the agent verifies its conclusions before finalizing its response. In summary, ASearcher demonstrates expert-level search behaviors, including uncertainty-aware reasoning, precise information extraction, cross-document inference, and grounded verification. Section Summary. In this section, we outline our approach to multi-turn agentic reinforcement learning using a Markov Decision Process framework, highlighting the challenges faced by existing online RL methods in complex search tasks. We demonstrate how our agent, ASearcher Web QWQ, effectively decomposes queries, extracts precise information, and verifies conclusions, showcasing its superior reasoning capabilities compared to other models. Section: ASearcher. In this section, we introduce ASearcher, our open-source project aimed at enhancing search intelligence in search agents through extensive reinforcement learning training. ASearcher trains a search agent capable of addressing complex questions by thoroughly resolving uncertainties and making multiple tool calls. We will discuss the agent's design, the training data, the data synthesis agent, and the fully asynchronous reinforcement learning training involved in ASearcher. For the agent design, we utilize a straightforward approach. The agent can access 2 main tools, a search engine and a web browser. The search engine processes a text query and provides relevant snippets along with their URLs, while the web browser retrieves the content of a given web page. To effectively solve complex problems, the agent must cleverly combine these tools and extract essential information from the large data available. Web pages often contain lengthy content, so we have the agent summarize them into concise summaries. During training, we optimize this summarization process, allowing the agent to enhance its summarization skills through reinforcement learning. In ASearcher, we explore 2 types of search agent instantiations: base large language models, LLMs, like Qwen 2.5-7b, 14b, and advanced large reasoning models, LRMs, such as QWQ32b. Each type requires different design choices for managing history and prompting. For base LLMs, we follow previous methods by using an append-only style for prompting. This means we start with a system prompt and add all generated responses, search results, and web page summaries to the history. The agent then uses this complete history to produce reasoning texts and actions, ensuring efficiency during inference. For LRMs, which already have instruction-following capabilities, we provide different prompts for tool selection, summarization, and answering. Since LRMs can generate lengthy responses, we need to keep the input compact. Thus, we retain only summarized thoughts and tool calls in the history, providing the most recent 25,000 characters as context to ensure the LRM generates responses within a manageable token limit. We also emphasize that all responses generated by the agent, including its thought processes, tool calls, and summaries, are trained using an end-to-end reinforcement learning approach. Our training data comes from two main sources. First, we filter samples from open-source datasets to ensure they are challenging and of high quality. Second, we create high-quality question-answer pairs designed to help the agent learn effective search strategies. We start with training sets from Hotpot QA and 2Wiki Multi-Hop QA, both of which are multi-hop question-answer datasets. We use a model-based filtering process where we first train a model on the complete open-source data set with reinforcement learning. Then, we generate 16 responses for each question and filter out those that do not meet specific criteria, such as failing to find a correct answer or being too easy. This process allows us to retain only the most challenging questions, resulting in 16,000 samples for reinforcement learning training. Additionally, we develop a data synthesis agent to create high-quality question-answer pairs. This agent begins with a seed question and iteratively modifies it to increase complexity while ensuring alignment with reliable sources. It performs two key actions: injecting related facts into the question to enhance context and fuzzing details to increase uncertainty. We implement a rigorous quality verification process to assess the clarity, accuracy, and difficulty of the synthetic questions. After synthesizing questions, we filter out those that can be answered directly by the LRM without using search tools, as these do not contribute to improving search capabilities. Starting with 14,107 seed questions, we perform an average of 6.3 injections and 3.2 fuzzes per question, ultimately curating a final dataset of 25,624 entries, with each selected question averaging 4.27 injections and 2.10 fuzzes. Section Summary. In this section, we present ASearcher, an open-source project that trains a search agent using reinforcement learning to effectively solve complex queries by utilizing a search engine and web browser tools. We detail the agent's design, training data synthesis, and the end-to-end reinforcement learning process, emphasizing the creation of challenging question-answer pairs to enhance the agent's search capabilities. Section: Challenges of Scaling Up Trajectory Length in RL. In this section, we empirically demonstrate that complex tasks necessitate numerous tool calls, which means that reinforcement learning, RL, training requires a large turn limit to effectively train advanced search agents. We also observe that the execution time of trajectories varies significantly during training, potentially causing considerable idle time in batch generation RL systems. For complex tasks, we find that they often require extensive language model, LLM, generations and multiple tool calls to address intricate problems, resulting in longer trajectory execution times. Our evaluation of the QWQ32B agent on various benchmarks shows that accuracy improves with more turns, confirming that longer trajectories are essential for solving complex tasks. We note that long trajectories introduce substantial variability in execution time. Our analysis of tool calls and token generation during the training of our QWQ agent reveals that the longest trajectories can involve many more tool calls and significantly more tokens than shorter ones. This variation leads to unpredictable runtimes for each trajectory, complicating training efficiency. Both extended execution times and high variance in runtime negatively impact RL training efficiency. We illustrate this with the one-step-off RL training system, where trajectory generation and training occur simultaneously. Despite overlapping these processes, batch generation is still limited by the slowest trajectory, leading to GPU idle time and underutilization. To enhance the efficiency of agentic RL training, we implement a fully asynchronous training approach. This includes two key aspects: asynchronous trajectory rollouts and decoupled rollout and training. In our asynchronous trajectory rollouts, we collect trajectories in parallel without interference. Each trajectory independently sends requests for tool calls and LLM generations, allowing for concurrent processing by the servers. This independence ensures that one trajectory does not have to wait for another, thus improving training efficiency. Additionally, we fully decouple trajectory rollouts from model updates. In our fully asynchronous RL training, long trajectories do not block the generation process and can span multiple model versions, which significantly reduces GPU idle time and maximizes GPU utilization. Training steps commence as soon as enough trajectories are collected for a batch, allowing us to proceed with shorter trajectories without waiting for longer ones. We apply fully asynchronous agent rollouts to train ASearcher. Our approach involves decoupling trajectory rollouts from model updates, allowing for more efficient processing. Each model update occurs once a batch of trajectories is ready, and this decoupling prevents lengthy trajectories from hindering updates. Furthermore, trajectory rollouts are collected in parallel, with agents independently making requests to generation and tool servers. The underlying servers manage dynamic batching of these concurrent queries to enhance throughput. Finally, we adhere to the Markov decision process (MDP) formulation, defined by the tuple consisting of state space, action space, transition probabilities, and rewards. The state space includes history, search results, and retrieved web pages, while the action space encompasses the tokens generated by the agent. The transition probability describes how the state updates after an action is taken. At each time step, the agent receives a state and generates an action based on its policy, aiming to maximize the expected return over time. Section Summary. In this section, we demonstrate that complex tasks in reinforcement learning (RL) require longer trajectories due to extensive tool calls, which improves accuracy but also introduces significant variance in execution time, leading to inefficiencies. To address these challenges, we adopt a fully asynchronous training approach that decouples trajectory rollouts from model updates, allowing for improved GPU utilization and reduced idle time during training. Section: GRPO Training. In this section, we employ the GRPO algorithm to train our search agents. For each input question, we generate multiple trajectories, where each trajectory consists of a sequence of states and actions. To optimize our agents, we use a specific loss function that incorporates a hyperparameter and calculates the advantage for each trajectory based on the relative rewards within each group. To improve training efficiency, we implement dynamic filtering, which removes queries that do not provide useful training signals. This includes queries where all responses yield the same rewards, such as those where the agent already performs well or those with incorrect answers. For our reward function, we use a sparse reward approach, giving rewards only at the end of each trajectory. When training from base language models, we combine a format reward with the F1 score. For fine-tuning LRM-based agents, we use LLM as judge as the reward function and skip format rewards since these models naturally produce well-formatted outputs. We evaluate our agents on both single-hop and multi-hop question-answering tasks, using various datasets for each type. For single-hop questions, we utilize natural questions, trivia QA, and pop QA, while for multi-hop questions, we use hotpot QA, 2Wiki multi-hop QA, Musique, and Bamboogle. We also assess performance on more challenging benchmarks like Frames, Gaia, and Xbench Deep Search, sampling 1,000 instances from validation sets and using full test sets for others. Our evaluation involves two settings with different search tools. In the first, agents interact with a local knowledge base using a retrieval augmented generation system. In the second, They operate in a web-based environment with access to a search engine and a browser. For the more challenging benchmarks, we only evaluate in the web-based setting. We compare our agents against two groups of baselines aligned with the benchmark categories. For both multi-hop and single-hop tasks, we include various models and also prompt a model to generate answers directly without tools. For the challenging benchmarks, we compare against powerful models, ensuring all baselines are evaluated with the same tools for fairness. We use two evaluation metrics: the F1 score, which measures the balance between precision and recall at the word level, and LLM as judge, where a strong language model assesses the correctness of outputs based on specific instructions. For the challenging benchmarks, we report scores using only LLM as judge. Regarding training details for ASearcher, we set a term limit and batch sizes for different model scales. We prepare two training datasets, each containing 35,000 samples, and the training process for ASearcher Web QWQ takes approximately 7,600 GPU hours. Finally, we present our main results across three evaluation settings: local knowledge base with retrieval augmented generation, web-based search on standard benchmarks, and web-based search on more challenging benchmarks. ASearcher consistently outperforms existing open-source agents across various metrics, with ASearcher 14b achieving the best performance overall. These results demonstrate the effectiveness and scalability of ASearcher across different tasks and model sizes. Section Summary. In this section, we describe our use of the GRPO algorithm to train search agents, generating multiple trajectories for each input question and optimizing them through a specific loss function. We enhance training efficiency with dynamic filtering to exclude uninformative queries, adopt a sparse reward function for evaluation, and benchmark our agents against various QA tasks, demonstrating that ASearcher consistently outperforms existing models across different scales and settings. Section: Local Knowledge Base with RAG on Standard QA Benchmarks. In this section, we present our findings on the performance of ASearcher Local, which we trained using reinforcement learning with a local knowledge base. As shown in our table, ASearcher Local outperforms other models in both 7b and 14b configurations on various multi-hop and single-hop question answering benchmarks. Specifically, in the 7b setting, we achieve an average F1 score of 58.0, surpassing strong competitors like Search R1 to 7b and R1 Searcher 7b. We also note a loss J score of 61.0, again outperforming the same baselines. The advantages are even clearer in the 14b setting, where ASearcher Local 14b reaches an F1 score of 60.0 and a loss J score of 65.6, exceeding the larger 32b baseline. Next, we evaluate our models in a realistic web-based environment. Here, we test models trained solely with a local knowledge base in a zero-shot manner to assess how well the search strategies learned through reinforcement learning generalize. Across both model sizes, ASearcher consistently outperforms strong baselines. Notably, ASearcher Web 14b achieves the highest performance with an average F1 score of 61.5, surpassing the strongest 32b baseline. ASearcher Local 14b also shows impressive generalization in the web setting, significantly outperforming all comparable or larger baseline models in terms of loss J, confirming that ASearcher learns adaptable search strategies. We also report results on challenging QA tasks that require advanced problem-solving and search strategies. These benchmarks test our agent's ability to interact with the web and retrieve current information beyond the internal knowledge of large language models. Our agent, ASearcher Web QWQ, achieves the best average scores on Gaia and Xbench Deep Search, outperforming previous state-of-the-art open-source agents. Additionally, we measure the pass-at-4 score, which indicates the success rate of finding correct answers, where ASearcher Web QWQ also excels compared to other agents. Regarding the effect of reinforcement learning training, we observe significant improvements in scores on Gaia, Xbench Deep Search, and Frames. The pass-at-4 score also shows notable gains, particularly on Xbench Deep Search, indicating that our training effectively teaches the agent complex search strategies for precise information retrieval. We analyze the training dynamics of ASearcher Local 7B and ASearcher Local 14B, noting an increase in generated tokens, search queries, and web page browsing throughout training. The number of search queries reaches up to 6, which is higher than previous reports. However, we find that the 7B model struggles with web page browsing, while the 14B model successfully learns to access web pages for challenging questions later in training. We suspect that the 7B model's limited capacity hinders its ability to summarize lengthy web pages effectively in a zero-shot reinforcement learning setting. Lastly, we examine the training dynamics of ASearcher Web QWQ, where we see the agent increasing its tool calls, peaking at around 40 calls by the 200th step, with some instances reaching up to 70 calls. The QWQ32B agent also generates a substantial number of tokens, exceeding 150,000. This trend in tool usage and output length underscores the potential of fully asynchronous reinforcement learning training for complex real-world applications. Section Summary. In this section, we demonstrate that ASearcher Local, trained with a local knowledge base, outperforms strong baselines on various QA benchmarks, achieving significant F1 and LOS-J scores, particularly at the 14B scale. Additionally, ASearcher Web QWQ shows strong generalization in web-based settings, excelling in challenging QA tasks and demonstrating effective learning of complex search strategies through reinforcement learning. Section: Search Agents. In this section, we discuss the development of agent workflows that allow large language models, LLMs, to use external tools for tackling complex tasks, with examples like Search01 and Reagent. While prompt-based methods are useful for quick development, they are limited by the capabilities of the LLMs and do not improve reliably with feedback from the environment. Some researchers are working on creating supervised fine-tuning, SFT, trajectories for LLMs, using large models to generate retrieval and reasoning paths to refine smaller models. Recently, there has been a focus on using reinforcement learning, RL, to boost LLM-based agents, particularly in multi-hop question-answering benchmarks like Hotpot QA and 2Wiki multi-hop. Studies have shown that RL training with multi-hop QA data increases tool usage. RAGR1 combines SFT and RL to improve search strategies. More recently, we have seen efforts to tackle more difficult tasks by fine-tuning advanced prompt-based agents powered by large reasoning models through offline RL, SFT on simulated paths using real web data, and creating challenging questions for RL training. Regarding synthetic data for search agents, we note that instead of depending solely on extensive human annotation, data synthesis has become a scalable method for preparing training data. Recent techniques generate realistic question-answer trajectories by interacting with actual web pages and curating data using large reasoning models. Additionally, WebSailor creates structurally complex tasks through sampling and fuzzing, while WebShaper employs set theory techniques to develop high-quality complex questions. In contrast, ASearcher builds an autonomous LLM agent that synthesizes challenging questions with high uncertainty, without needing complex knowledge graphs. Both the data synthesis agent and the synthetic training data from ASearcher are fully open-sourced.